So hello everyone, welcome to the channel. So in this video I'm gonna show you the basics of open channel hydraulics using HEC RAS 2D for flood modeling. So now let's get started. So what is the open channel hydraulics? So open channel hydraulics studies how a water flows in natural or a man-made channel where the surface is exposed to air like river, canal or drainage systems. So unlike pipes which are fully enclosed, the open channel have a free surface that moves under gravity. So this type of flow is called as a free surface flow or a gravity driven flow. So the examples of the open channel hydraulics, which includes river and streams and irrigation canals and stormwater drains. So the different open channel hydraulics are given in this figure, you can able to see. So which includes rivers, canals, streams and sewage systems. So hydraulics is the science of managing liquids like water in motion and combining the engineering and physics principle to design and analyze the water system. So the open channel, which includes the river, canal, streams and sewage system, so which is shown in this figure. So now let us take a look at the hydraulic parameters. So understanding the hydraulic parameters in river. So open channel flows depends on the key hydraulic parameter that describes the shape, size, movement of water in the river, canals or streams. So the three important hydraulic parameters, which includes the depth. So the vertical distance from the water surface to the channel bed. And next hydraulic parameter is the width, the horizontal distance between the two banks. And the third parameter is the velocity. So the speed of water flow, so usually in meter per seconds in as a unit. So from figure in the right side top, you can able to see this figure. So which includes the width and the water depth and velocity, and this includes the measured stream length, and this is the cross-sectional area. And to calculate the discharge of the river, so we're going to use this particular formula, that is discharge equals to area multiplying velocity. So we have to calculate the area multiplying the velocity of the river in order to calculate the discharge. So in the second figure, so you can able to see here. So in this figure, so this particular so from the left bank to the right bank, so this particular area is called as a bank full width, and followed by the channel width starts from here. So where the water makes the contacts with this the sandbar here, the water contact from this part to the water contact in the right bank. So it is called as the channel width. And the next one is the channel depth. So you can able to see from the top surface to the bottom surface of this the river channel here. So it is called as the channel depth here. And the next parameter is the wetted parameter. So the total length of the river channel in contact with the water in the cross section. So here this particular red line here, which indicates the wetted parameter, and the definition is given here: the total length of the river channel in the contact with the water in the cross section. So this area is called as this red color, which is indicated here, which indicates the wetted perimeter. And in order to calculate the cross-sectional area, so in order to calculate the cross-sectional area of this particular the river channel here, so to do that we're going to mention the width multiplying the depth. So the width which includes from this left bank to the right bank, which is called as the width, and the depth which represents from this top surface of the water to the bottom surface of this river channel here, so it is called as the depth. So to calculate the cross-sectional area, we're going to use width multiplying the depth. And the next step, to calculate the discharge of the river, we're going to use the cross-sectional area. So we're going to use this particular one here as a cross-sectional area multiplying velocity. So it's going to give us the discharge. And followed by the hydraulic radius. So to calculate the hydraulic radius, we're going to use the cross-sectional area multiplying the wetted parameter. So we have to use to calculate the hydraulic parameter, we're going to use the cross-sectional area multiplying the wetted perimeter. And usually the width which is indicated in inch, feet or in meters, and the depth which usually indicated in inch, feet or a meter, and the velocity can also be indicated in feet per second or meter per second. And in this figure you can able to see the different parts of this the river. So starting with the left bank height, so from so this is the water the left bank height here, so which is usually calculated from the water level. So you can able to see this imaginary line, the dotted line here. So from this part to the top surface of the bank here, which is called as a left bank height, and similarly towards the right side, so the from the water level to the top of the bank, which indicates the right bank height. And in case we have any embankment here, so usually it can be indicated as like this, so which is called as a right embankment height, and followed by we have some sidebars here. So this particular is called as a sidebar, so which is usually sediments which is accumulated here. And the water width, so the water width start from this left side to the right side of the water presence, which is indicated as the water width, and followed by the channel width starts from the left side left bar to the right bar, so which is called as the channel width. And during the time of flood, the water can be rise to this level here, which is indicated in this dotted imaginary line here, the water level line. So why do these hydraulic parameter matters? So discharge helps to predict the flooding risk, and the hydraulic radius, which indicates how easily the water flows. So the higher, which is more efficient, and last is the velocity, which affects the erosion and sediment transport. So for example, let us consider an example. So if a river has a width of 10 meters and a depth of 2 meters and a velocity of 1.5 meter per seconds, so we have to calculate the cross-sectional area and the discharge here. So we can able to see from this figure here, so width will be, this is called as the width, and from the left bank to the right bank, which is called as the width, and followed by the depth, which indicates from the top level of the water to the bottom of the river channel here, so which is width. And the velocity is the speed at which the water travels here. So the formula for to calculating the cross sectional area, which is indicated here, the depth multiplying width, and followed by to calculate the discharge, so we're going to use area multiplying velocity. So to calculate the cross-sectional area, so we're going to use this particular formula, that is depth multiplying width. So the depth is 2 meters and the width is 10 meters. So the cross-sectional area, so we're going to multiply 10 multiplying 2, it's going to give us 20 meters square. So it is the cross-sectional area, and followed by to calculate the discharge, the formula is area multiplying velocity. So to calculate the discharge of the river, we're going to use the cross-sectional area multiplying the velocity. So the discharge is equals to 20 meter square, that is the cross-sectional area. We're going to multiply with velocity of the river, that is 1.5 meter per second. So it's going to give us the discharge here, that is 30 meter cube per second. So this is the discharge. So this river has. So now we're going to take a look at the river cross-section properties here. So we have this following the river cross-section properties, starting with the bank full width, so which indicates the width of the channel when a water fills it to the top of the banks, and followed by the channel depth. So the channel depth which indicates the average depth of the water in the channel, and followed by we have the cross-sectional area. So the total area through which the water flows, that is usually which is indicated in the formula, the cross-sectional area is equals to the width multiplying the depth. And the next, the fourth parameter is the discharge, that is the flow rate. So the volume of water passing through a point per second. So the usually which is indicated in this formula, the discharge equals to cross-sectional area multiplying the velocity. And the fifth cross-sectional property is the hydraulic radius. So the hydraulic radius, which indicates the the efficiency of the flow, the area divided by the wetted parameter. So the hydraulic radius is equals to the cross-sectional area divided by the wetted perimeter. And last is the wetted perimeter, the length of the channel bed and the sites in contact with the water. So it is called as the wetted perimeter. So you can able to see from this figure, we have the flow, the bank full width, and the width here, and the depth, and the wetted perimeter. So this is the water in contact with the channel beds. It is called as the wetted perimeter. So as you can able to see, the discharge's formula is velocity multiplying the cross-sectional area. And similarly, to calculate the velocity, if you have the distance and the time, so you can calculate the velocity of the river. So this particular figure, which shows is the river cross-section extracted from the Aster Global Digital Elevation Model. So version 2, the data exhibiting the section type at the altimeter crossing the site for the rivers. For example, the figure 1, which indicates the river cross-section for the Mississippi. So this is the cross-section of Mississippi River here. And similarly, so this is the river cross-section in Congo. And next is this is a river cross-section of Amazon. And next is a river cross-section of this particular one here, that is Negro. And the next is the Amazon here, that is Antonio. So this is a cross-section here. So each of this cross-section which indicates, which tells us the different information about this particular river cross-section here. And last is Lena here. So you can able to see the cross-section here. So these are the different river cross-sections. I could like to have shown you the different river cross-section which is done using the Aster Global Digital Elevation Model. And this is the figure which indicates the river cross-section. Second figure which indicates the river transient area. So the first figure which indicates the river cross-section here. So you can able to see the river has a different cross-section at each course of its so the river goes from the starting point to its ending point. So the ending point here you can able to see is completely flat. So which might indicates the river has reached the coastal part of the area. So the completely flat terrain here which can be observed. And from the figure 2 which indicates the river transient area. So the kilometer from the ITT dam here. So here the figure A which indicates the cross section of the river at this point. And figure B which indicates the cross section of the river in this point here from a kilometer from ITT dam starting from 0 to 400 kilometers. And last is the H which is indicated here. So this particular river cross section is completely flat here. So this is the river cross section, and second figure is a transient area. So next we're going to focus on the hydraulic parameters. So the hydraulic parameter helps us to measure and predict how the water moves through a river and channels. So the basic measurements, which includes the depth and how deep the water is from the surface to the riverbed. And the second parameter, it is the width, the distance between the two river banks, and followed by the velocity, the speed of the flowing water, that is usually measured in meter per seconds. So first let us take a look at the velocity measurements. So the velocity measurement, the velocity will change along the course of river and is determined by the factors such as the gradient, the volume of water, and the shape of the river channel, and the amount of friction created by the bed rocks and the plants. So usually we're going to use this Manning's equation to estimate the velocity based on the channel shape and roughness. So which is given by this particular formula, that is V equals to R to the power of 2 by 3 multiplying S to the power of 1 by 2 divided by N. So the V which indicates the velocity in meter per seconds, and R which indicates the hydraulic radius, the flow efficiency, and the S which indicates the slope of the riverbed, and N which indicates the roughness coefficient. So higher the N value, the more friction is. For example, the rocky beds. So the velocity, it can be measured by various methods such as the current meter. So example is the vertical axis current meter, like an underwater windmills. So it floats as a lightweight objects which is timed over the distance. So the vertical axis current meter is a hydraulic instrument which is used to measure the flow velocity in the open channel example river, canals, and pipes. So unlike the horizontal axis meter, so its rotor spins around the vertical shaft, making it ideal for the shallow or an irregular channel, and the low velocity flows less than 0.5 meter per seconds. So the field studies where the portability is key. So the next parameter is the depth measurements. So the depth can be measured, the average water depth. So it is calculated by the cross-sectional area divided by the channel width. So it is the ratio of width and the area of the cross-sectional area. So which is indicated in this formula. The depth equals to the cross-sectional area divided by the width. So this is the width, and this is the cross-sectional area of this river. And the right side figure, which indicates the vertical axis current meter, and this is a different part of this vertical axis current meter, and this is the image of the vertical axis current meter. So the next parameter is the width measurement. So the width of the river is the distance between the 2 points on the side of the river times the tangent of the angle. So this can also be solved by using any 2 points on your bank of the river. So the width here, which indicates this is the width of the channel here, so which is clearly indicated in this diagram here. So the next parameter is the stream discharge. So the flow of the water through a stream channel is called as a stream discharge. So in the most countries, it is measured in cubic meter per second. And the following equation which defines the stream discharge mathematically. So to calculate the stream discharge, that is V multiplying, that is V is the average velocity, multiplying the width, multiplying the depth to calculate the stream discharge. So for example, if a river is a 10 meter wide and 2 meter deep and flows at 1.5 meter per second, so let us calculate the discharge, stream discharge. So to calculate stream discharge, Q equals to, we're going to mention the velocity 1.5 meter per second multiplying with the width, that is 10 meters, and multiplying with the depth, that is 2 meters. So it's going to give us the discharge of 30 meter cube per second. So that's like a 30 bath tubes of water passing by every second. So next we're going to understand the velocity distribution in the open channel using the Manning's equation. So the Manning equation is a fundamental tool in hydraulic engineering to estimate the flow velocity in channels, but its results vary significantly across the different channel types due to the difference in shape, roughness, and the flow characteristics. So why the Manning's equation gives a different result? So the channel first is the channel geometry. So the narrow channels versus the wide channels have a different friction patterns. Example is a narrow rectangular channel. The depth divided by the width is greater than or equals to 5 and has a higher friction from the side walls and slowing the flow. And the next is the roughness. So the smooth concrete versus the natural irregular bed alters the velocity. So the smooth concrete has the higher velocity and lower friction versus the natural irregular beds has a higher friction with low velocity. And next is a flow type. So a turbulent flow has a chaotic velocity fluctuations, while the laminar flow is a smoother. So the key factors affecting the velocity distribution. So the first factor is the channel shape. So the triangular channels concentrate the flow at the center, and the natural channels have irregular velocity profiles. So next is the depth versus the width ratio. So the narrow sections have a uniform flow, while the wide sections develops a lateral velocity gradient. And the next is a bed roughness. So the rocky bed reduces the near bed velocity, and the smooth beds allows a faster flow. And last is the pressure distribution. So the pressure is higher in the deeper section and accelerating the flow vertically. So the velocity profiles in the different channels. So you can able to see we have this different channel types. For example, the triangular channel, trapezoidal channel, and the narrow rectangular section, and the shallow ditch, and the pipe, and the last is the natural irregular channel. So starting with the triangular channel, so the faster flow at the apex, that is at the center, and slower near the banks. So it is faster at the center, the velocity is higher at the center, and it's slower near the banks. And the next is the shallow ditch. So the uniform velocity due to the shallow depth, but slowed by the bed friction. So this is the shallow ditch. So uniform velocity is due to its shallow depth. So it is a shallow depth, but slowed by the bed friction. And the next section is the narrow rectangular section. So it is a near uniform velocity, but slowed by the side wall frictions. So this is the narrow rectangular sections. So it is a near uniform velocity, but it's slowed by the side wall frictions here. And the next section is the pipe. So it is fastest flow at the center. So the pipe is the fastest flow at the center and zero velocity at the walls. And last is the natural irregular channels. So it is unpredictable velocity hotspot due to the rocks and bends and vegetations. So this is a natural irregular channel. So it is an unpredictable velocity because of its due to the different rocks, bends and the vegetation which occurs in this natural irregular channels. So it's generally the velocity is unpredictable velocity, and this is the velocity distribution for the turbulent flow for the different channels. So we have seen the triangular channel, and next we saw the shallow ditch section, and the third is a narrow rectangular section, and fourth is a pipe, and last is the natural irregular channel. So next we're going to take a look at the concept of the Reynolds number. So to determine whether the flow is a laminar or the turbulent, we're going to use Reynolds number. So the Reynolds number is a dimensionless number used in the fluid mechanics and hydrology. So it is a ratio of inertial force to the viscous force in the liquid. So this number helps to predict the flow regime of the fluid, whether the flow is a laminar or a turbulent. So the general formula to calculate the Reynolds number is rho multiplying velocity multiplying the d, that is the depth, divided by the nu, that is the dynamic viscosity of the liquid. So the rho, which indicates the density of the liquid in kg per meter cube, and v is the average velocity of the fluid in meter per second, and the d is the characteristic length or the depth which is in the meters, and last is a nu. It's a dynamic velocity, a dynamic viscosity of the liquid in pascals or newton per second per meter square. And velocity. The higher velocity increases the Reynolds number, which means the flow tends towards the turbulence. The characteristic dimension. So this could be a pipe, a diameter, or a hydraulic depth, or other relevant length scale. The larger the dimensions favors the turbulence. And the next is the density. So the denser fluid increase the inertial forces, raising the Reynolds number. So which gonna indicate a turbulent, a higher Reynolds number, which indicates a turbulent flow. And last is a viscosity. So viscosity, so the higher viscosity provides the more internal resistance, which suppresses the turbulence and keeps the flow laminar. So the flow classification based on the Reynolds number. So for a laminar flow, the Reynolds number should be lesser than 2000. The flow is orderly and smooth, and the fluid particles moves in parallel layer with the minimal mixing. An example is the flow of a groundwater or oil. So the laminar flow, which is indicated in this figure here, so this is the laminar flow. And the next is the transitional flow. If the Reynolds number is lesser than 2000, so that is if the Reynolds number is greater than 2000 and it is lesser than 4000. So this is called as a transitional flow. So the flow is unstable and may switch between the laminar and the turbulent. And the last is the turbulent flow. If the Reynolds value is greater than 4000, so the flow becomes chaotic with the eddies and vortexes and intense mixing of fluid particles. Example is a fast flowing river or storm water channels. So the turbulent flow, which is indicated in this figure here, so you can able to see the difference between the laminar flow and the turbulent flow. So the laminar flow, if the Reynolds number is lesser than 2000, and the turbulent flow, if the value is greater than 4000, it is a turbulent flow. So this particular turbulent flow generally occurs at a higher Reynolds number and is unpredictable and disorderly. So in this video I have shown you the basics of open channel hydraulics. So in our next video I'm going to show you the types of flows in the fluvial hydraulics. So thanks for watching, and make sure that you subscribe to our channel and give us a like.